The universe whispers secrets in a language of ghosts. Billions of years ago, the fiery birth of everything created a cosmic fossil, a faint relic known as the Cosmic Neutrino Background. This is not just ancient light, it is a sea of phantom particles passing through you right now, holding 25 profound mysteries about reality itself. By the end of this journey, you will understand how these cosmic ghosts could rewrite our entire story of the cosmos. We will explore whether they hold the key to dark matter, and if they can reveal what happened in the very first second of time. What cosmic secret do you hope is hidden within this primordial whisper? These cosmic whispers are nearly impossible to hear. The first and most fundamental mystery is simply catching them. The cosmic neutrino background is a sea of the oldest neutrinos, and they possess almost no energy. After traveling for billions of years, the expansion of the universe has stretched their wavelengths and sapped their strength, leaving them incredibly cold and sluggish. They are cosmic ghosts that have all but faded away. To detect them, we need technology that can sense the faintest of nudges, the most minuscule transfer of energy imaginable. This is the monumental goal of experiments like PTOLEMY, which aims to capture these relic neutrinos not by seeing them but by weighing them. The concept is to use a tiny piece of tritium, a special form of hydrogen, and watch it with unimaginable precision. If a relic neutrino interacts with a tritium nucleus, it would cause the nucleus to decay in a very specific way, releasing an electron with a precise amount of energy. The detector must be so sensitive it can measure the energy of that single electron to an accuracy of better than 1 part in 100,000. It is like trying to hear a single snowflake land on a quiet street during a roaring hurricane. Every form of interference, from cosmic rays to the natural radioactivity in the very walls of the detector, creates a deafening noise that drowns out the faint signal we seek. This is why these detectors are often built deep underground, shielded by miles of rock in a desperate attempt to find silence. We are pushing at the very edge of quantum measurement and material science, forced to invent tools that can perceive the imperceptible. What other secrets of the quantum world must we master to finally listen to this ancient, fading whisper from the dawn of time? Even if we could capture these phantoms, their very nature presents a second, deeper puzzle. We know they are cold, but exactly how cold should they be? The answer is written in the ancient laws of the Big Bang. The theory gives us a precise prediction for the temperature of the cosmic neutrino background, a frigid 1.95 degrees above absolute zero. This number is not a guess, it is a direct consequence of the universe's explosive expansion and cooling. As the primordial fireball grew, it stretched the wavelengths of those first neutrinos, cooling them down in a predictable and calculable way. Yet this calculation rests upon pillars we assume are solid. What if they are not? The predicted temperature depends on the exact sequence of events in that first second, on how many kinds of particles existed, and on the very rate of the universe's expansion. A measurement that deviated from 1.95 Kelvin, even by a tiny amount, would send shockwaves through cosmology. It would be a direct signal that our model of the Big Bang is incomplete. Perhaps an unknown particle species contributed to the early heat, or a fundamental force behaved differently than we thought. It could even hint at a deeper connection between neutrinos and the mysterious dark energy accelerating the cosmos. Finding the true temperature is like checking the universe's birth certificate against our theoretical predictions. A perfect match would be a monumental confirmation of our cosmic story. But a mismatch, a temperature that is slightly warmer or colder than expected, would be far more exciting. It would force us to rewrite the first chapter of everything, revealing that the dawn of time held physics we have yet to dream of. The temperature of these cosmic relics is not the only secret they guard. Their very identity is a puzzle written into the fabric of reality, one that leads us to the third great mystery. We know neutrinos have mass, a discovery that shattered the old standard model of physics, but we do not know how that mass is arranged. Think of the three known types of neutrinos as three siblings. We know their collective weight, but we do not know which one is the heaviest. This is the problem of neutrino mass hierarchy. There are two possibilities, and the fate of our cosmic story hinges on which one is true. In the normal hierarchy, the siblings are arranged as you might expect. There is a lightest one, a middle child, and a heaviest one. It is a straightforward family tree. But nature might prefer the dramatic. In the inverted hierarchy, the order is flipped. The two lightest neutrinos become nearly twins in mass, and they are both heavier than the third. It is as if the cosmic rulebook was written upside down. This is not just a minor detail. The correct hierarchy determines how neutrinos shaped the universe's largest structures and influences why we have more matter than antimatter. Current experiments on Earth are locked in a fierce competition to solve this, but they face a monumental challenge. The differences in mass are so vanishingly small that teasing them apart is like trying to weigh a single atom with a bathroom scale. This is where the ancient sea of the cosmic neutrino background offers a unique solution. These relic neutrinos are not all the same. Because they froze out of the cosmic soup so early, their populations bear the subtle imprint of which mass hierarchy was in place at the dawn of time. The way these phantoms interact with matter today, and the very patterns they would create in a detector like PTOLEMY, would be different for the normal versus the inverted scenario. It is a faint signature, a cosmic fingerprint left behind from the first second. By finally listening to this primordial whisper, we would not just be detecting a particle. We would be reading a classified document from the universe's birth, one that clearly states the true order of reality. Finding this answer would complete a chapter in physics we have been trying to write for decades. What other fundamental laws are written in the silent language of these ancient ghosts? But the story of these ancient particles does not end with their individual identities. A fourth mystery pulls our gaze from the single phantom to the cosmic crowd, asking where these neutrinos have gathered over the eons of cosmic history. The universe is not a smooth soup, it is a web of vast structures with galaxies and clusters forming at the dense intersections of this cosmic network. Each of these structures sits within a massive halo of dark matter, a gravitational well so deep it can bend space itself. The question is, did the cosmic neutrino background, this sea of ghosts, get pulled into these wells? Did these nearly massless particles, famous for barely interacting, actually cluster around the galaxies we see today? The theoretical predictions are a battlefield of ideas. Some models suggest that relic neutrinos, despite their incredible speed, would have been slowed just enough by the immense gravitational pull to form a diffuse, hot cloud around these dark matter halos. This would create a tenuous neutrino atmosphere enveloping every galaxy, a ghostly echo of the luminous structures we observe. Other theories argue the opposite, that their tiny mass and high velocity would have let them stream almost freely through these gravitational traps, leaving the distribution of the cosmic neutrino background nearly as smooth as it was at the dawn of time. The implications of this clustering are profound. If these relic neutrinos do gather significantly in these halos, they would contribute in a small but measurable way to the total mass of a galaxy cluster. This would force us to revise our precise calculations of how much dark matter is truly out there. It blurs the line between the known and the unknown, suggesting that a fraction of what we call dark matter could, in fact, be the accumulated weight of countless ancient neutrinos. Furthermore, the pattern of this clustering would be a direct record of the universe's growth. The way structures pulled in these particles over billions of years is a story written in their distribution, a narrative that could confirm or refute our entire model of cosmic evolution. Solving this mystery means we are not just looking for particles, we are mapping the invisible architecture of the cosmos. tracing how the faintest echoes of the Big Bang were woven into the grand tapestry of galaxies. What other invisible currents have shaped the universe we see today? This cosmic fingerprint leads us to an even grander enigma, one that questions our very existence. Why is the universe made of matter at all? The laws of physics, as we understand them, suggest the Big Bang should have created equal amounts of matter and antimatter, which would have annihilated each other in a flash of pure energy, leaving behind a cosmos of light and nothing more. The fact that we are here, that stars and planets and people exist, is proof that something broke that perfect symmetry. Some process in the earliest moments tipped the scales, leaving behind a tiny surplus of matter, 1 part in a billion from which everything we know was built. That pivotal event is known as leptogenesis, and its secret may be written in the ghostly patterns of the cosmic neutrino background. Leptogenesis is a compelling idea that places the neutrino at the very center of this cosmic crime story. The theory suggests that in the searing heat of the infant universe, heavy, unstable relatives of the neutrino decayed. Crucially, these decays did not produce matter and antimatter in equal amounts. For every billion antimatter particles, they produced 1 billion and 1 matter particles. This tiny 1 in a billion bias was the seed for every galaxy we see today. But how could we ever prove such an event occurred? This is where the ancient sea of relic neutrinos becomes a time capsule. The properties of the neutrinos we would detect in the cosmic neutrino background, their masses and the way they oscillate between types, are direct descendants of those first decisive decays. The specific pattern of masses, the very hierarchy we seek, is a fossilized record of the physics that drove leptogenesis. If the relic neutrinos tell us the mass hierarchy is inverted, for instance, it would strongly point toward a specific version of how this matter-creating event unfolded. It is as if the universe left us a single, faded photograph from the crime scene. By analyzing the subtle details in this cosmic fossil, we could finally understand the mechanism that allowed anything at all to exist. The phantom particles passing through you are not just silent witnesses to the universe's birth. They are the living heirs to the process that made your existence possible. What other answers about our own origin are encoded in this silent, pervasive sea? The very existence of this ancient sea rests on a startling assumption that neutrinos are eternal. But what if they are not? The sixth mystery challenges this core belief, probing the controversial idea that neutrinos might be unstable, decaying over cosmic timescales. We have always treated them as near-immortal ghosts traveling for billions of years unchanged. Yet some theories in physics suggest they could slowly disintegrate, transforming into even lighter, more elusive particles or perhaps even pure energy. If this is true, the cosmic neutrino background we hope to detect would be a ghost of a ghost, a dramatically thinned-out population of its original self. The expected signal in our detectors would be fainter or have a different character altogether. A search for this decay is a search for new laws of physics. The standard model of particle physics insists that neutrinos should be stable. Finding evidence that they are not would shatter that model completely. It would imply that neutrinos interact through forces we have never seen, forces that only reveal themselves over the immense span of cosmic history. The signature of this decay would not be a sudden burst, but a subtle distortion in the energy spectrum of the relic neutrinos we finally capture. It would be like listening for a specific chord in a symphony, only to find one of the notes is perpetually flat. That missing note would tell us that the orchestra is playing by a different set of rules. The implications ripple outward. If neutrinos decay, it could solve other puzzles, like the precise amount of dark matter or the unexpected patterns seen in high-energy cosmic neutrinos. To discover that these fundamental building blocks are not permanent is to discover that the universe is even more dynamic and mysterious than we thought. The silent sea passing through you might be slowly evaporating, and in its quiet fading, it could be whispering the secrets of an entirely new physics. Yet the potential decay of these phantoms is not the only way they could rewrite our story. A seventh mystery lies in a single, crucial number from the dawn of time, a value known as the neutrino chemical potential. This is not a measure of temperature or mass, but of a primordial imbalance. It asks a profound question: were there, from the very beginning, more neutrinos than antineutrinos? In the first second of the universe, the cosmic soup was a seething, dense plasma of particles and radiation. Within that chaos, a slight excess of one type of particle over its opposite would have been imprinted as a chemical potential, a kind of cosmic pressure favoring matter over antimatter, specifically within the neutrino family. We do not know if this imbalance existed. Our current models often assume it was zero, that the numbers of neutrinos and antineutrinos were perfectly equal. But that is an assumption of convenience, not a proven fact. Finding a non-zero chemical potential would be like discovering the universe was born with a slight tilt, a fundamental preference that was baked into its initial conditions. The cosmic neutrino background is the only place we can look for this fossilized evidence. The properties of these ancient neutrinos, their distribution and how they interact, would carry the indelible mark of that initial bias. A significant chemical potential would have altered how these ghosts froze out of the primordial plasma, changing their final temperature and density in ways a sensitive experiment could, in theory, detect. It would force us to confront a new origin story. Perhaps the matter-antimatter asymmetry we see today did not arise solely from a dramatic process like leptogenesis. Maybe the seed was planted even earlier, written directly into the universe's initial state as a fundamental preference for neutrinos over their antimatter twins. Constraining this number is like trying to read the cosmic ledger from the first instant to see if the books were always slightly unbalanced. A zero finding would point toward later dynamic processes as the source of everything. But a non-zero finding would suggest the universe was never perfectly symmetrical, that the preference for existence over nothingness was a fundamental feature of reality from time zero. What other foundational biases were built into the fabric of our cosmos at its birth? This very silence of the neutrino, its legendary reluctance to interact, may be its greatest deception. We now arrive at a mystery that connects the known ghost to the ultimate unknown, probing a tantalizing possibility. What if the relic neutrinos of the cosmic neutrino background are not entirely blind to dark matter? Theoretically, these two shadowy components of the cosmos should pass through each other like phantoms in the night, one governed by the weak nuclear force and the other by a mystery force we have yet to discover. Yet some compelling models suggest a bridge could exist. Certain theories, like those involving a hypothetical particle called a majoron, propose that neutrinos and dark matter particles could talk to each other through a new, incredibly feeble force. This would not be a strong interaction, but a whisper so soft it has evaded all our experiments so far. How would such a secret conversation manifest? The evidence would be written in the patterns of the cosmic neutrino background itself. If relic neutrinos and dark matter particles scatter off one another, even rarely, it would leave a subtle imprint. This interaction could prevent the neutrinos from clustering around galaxies as much as they otherwise would, effectively smoothing out their distribution. Alternatively, it could transfer a tiny amount of energy, slightly warming the ancient neutrino sea in regions of high dark matter density. These effects would be minute, a faint statistical anomaly in the data from a future detector. But finding that anomaly would be like discovering a secret door. It would give us our first tangible clue about the nature of dark matter, not by detecting it directly, but by seeing how it subtly brushes against something we are desperately trying to measure. The cosmic neutrino background would transform from a fossil into a probe, a tool for mapping the invisible dark matter halos of galaxies by the very shadows they cast upon this ancient sea. The ghosts would finally be telling us not just about themselves, but about the darker ghosts that hold the universe together. What other invisible dialogues are happening all around us, hidden in the quietest signals of the cosmos? The silent whispers of the cosmic neutrino background may carry echoes from a time even before the neutrinos themselves were born. To understand the universe's first moments, we must confront its most spectacular growth spurt, a period known as cosmic inflation. Theory tells us that a fraction of a second after the beginning, the entire cosmos underwent a violent, exponential expansion, stretching a subatomic speck of space into a vast universe. This event smoothed out the cosmos and planted the seeds for all future structure, but its energy scale and exact mechanisms remain among the greatest unsolved puzzles in physics. We have one primary fossil from this era, the cosmic microwave background, the ancient light that fills the sky. Yet this light only gives us a snapshot from 380,000 years after the Big Bang. The cosmic neutrino background offers us a window that opens much, much earlier. These relic neutrinos decoupled from the rest of the cosmic soup a mere 1 second after the beginning, making them messengers from a time vastly closer to the inflationary burst itself. How could these ancient particles possibly tell us about an event that preceded them? The answer lies in the most subtle of imprints, the statistical patterns woven into their very fabric. Inflation is believed to have generated not just density fluctuations, but also primordial gravitational waves, ripples in the very fabric of spacetime. These waves would have left a distinct signature on all the matter and radiation that followed, including the neutrinos. While the cosmic microwave background gives us one view of these waves, its picture is blurred by the interactions of the later plasma. The neutrinos, by decoupling so early and interacting so weakly, would have preserved a cleaner, more pristine record of these primordial tremors. Their distribution across the sky would carry a unique statistical fingerprint, a specific pattern of correlations that could confirm the inflationary origin of these waves and crucially reveal their strength. The amplitude of these waves is directly tied to the energy scale of inflation itself. It is a number that tells us how powerful the universe's engine was during that first, incredible moment of growth. By decoding the subtle patterns in the cosmic neutrino background, we could measure this energy scale directly. This is a measurement the cosmic microwave background alone may never provide with certainty. It would be like comparing a faded, ancient photograph to a high-resolution scan. The neutrino background offers the potential for a scan of the universe's infancy, revealing details about the inflationary force that are otherwise permanently locked away. Finding this imprint would not just confirm inflation, it would tell us what drove it, taking us from a vague idea of a growth spurt to a precise understanding of the physics that powered the birth of everything we see. What other fundamental forces were at play when reality was less than a second old? These faint cosmic ghosts are not spread perfectly smooth across the sky. Just as the cosmic microwave background is not a uniform sheet of light but bears a pattern of hot and cold spots, the cosmic neutrino background is also expected to display its own intricate map of anisotropies. These are tiny variations in the density and temperature of the ancient neutrino sea, a ghostly fingerprint of the universe's earliest structures. The source of these patterns lies in the primordial chaos of the first second. When the neutrinos decoupled, they were flying through a universe that was not perfectly uniform. Minute differences in density, gravitational potential, and velocity were already imprinted on the cosmos from its inflationary birth. As the neutrinos streamed outward, these initial conditions sculpted their paths, creating a specific pattern of overdensities and underdensities frozen into their distribution. The expected anisotropies in the neutrino background, however, would be fundamentally different from those in the light-based CMB. The CMB patterns were shaped by a complex tug-of-war between gravity and radiation pressure in a thick plasma, a process that created the famous acoustic peaks we observe today. The neutrinos, by contrast, were almost free from this struggle. their weak interactions meant they behaved more like a collisionless fluid, streaming freely away from dense regions. This creates a smoother, more subdued pattern of anisotropies, one dominated by the subtle effects of gravitational redshifts and their own intrinsic thermal motions. Decoding this specific pattern would be like reading a different page from the same cosmic history book. It would tell us about the initial density fluctuations at a much earlier time, offering a pristine view of the universe's raw potential for structure before later processes complicated the picture. The statistical properties of these neutrino anisotropies would provide a powerful, independent test of the inflationary paradigm. Do they match the predictions of a Gaussian random field, as inflation suggests, or do they reveal unexpected correlations, hints of physics from before the Big Bang? Furthermore, by comparing the neutrino map to the light map, we could see how structures evolved between 1 second and 380,000 years. This is a direct measurement of the universe's growth during its most mysterious, dark age. The silent sea is not a featureless void, it is a detailed, though incredibly faint, blueprint. Its subtle ripples and valleys are the infant form of the great cosmic web, the earliest sketch of the galaxies and voids we see today. What would it reveal about the true seeds of our own galactic home? These cosmic ghosts may not be as solitary as we once believed. The 11th mystery forces us to consider a radical possibility, that neutrinos might possess a secret social life, interacting with each other through a hidden force all their own. We have always pictured them as lone wanderers, passing through worlds and each other without a trace. But what if they whisper amongst themselves? This idea of neutrino self-interactions proposes that these particles could scatter off one another through a new, unknown mediator, a force that operates entirely within the ghost realm. The implications for the ancient cosmic neutrino background are profound. In the standard story, when neutrinos decoupled a single second after the Big Bang, they effectively stopped talking to everyone, including their own kind. They streamed freely into the expanding universe, their distribution shaped only by gravity and their initial thermal motion. But if a secret force existed, it would have kept them in conversation for a little while longer. This extended dialogue would have reshaped their entire cosmic journey. Think of a crowd of people released into a vast field. Without self-interactions, everyone just runs in their own initial direction. But if they can still push and pull on each other, they will form into looser groups, smoothing out the most extreme differences in their density. For the relic neutrinos, this means that any secret force would have acted as a kind of cosmic pressure, erasing the finest, sharpest details in their distribution. The anisotropies, the subtle hot and cold spots in the neutrino background, would be noticeably smoother than our standard predictions. The expected map would be less textured, as if viewed through a slightly frosted glass. This is a signature a future detector could potentially look for. A smoother than expected neutrino sky would be a direct hint of this hidden sociability. Furthermore, these self-interactions could have altered how the neutrino sea responds to gravity. A self-interacting fluid would clump differently around the seeds of cosmic structures, potentially leaving a distinct mark on the large-scale distribution of galaxies we see today. It blurs the line between a particle and a collective phenomenon. Finding evidence for this would mean that the phantom particles passing through you are not just independent entities, but part of a subtle, interconnected network, a society of ghosts with its own private rules. What other clandestine conversations are these ancient particles having right under our noses that could rewrite the rules of their cosmic behavior? The same hidden forces that gave neutrinos a secret social life might also connect them to the most terrifying objects in the early universe. We now journey to the 12th mystery, a shadowy link between the cosmic neutrino sea and primordial black holes. These are not the black holes formed from dying stars, but hypothetical monsters born in the unimaginable density of the universe's first moments. If they existed, these primordial black holes would have been seeds of pure gravity scattered throughout the infant cosmos. Their potential connection to the neutrino background is a tale of two possibilities, each more fascinating than the last. The first scenario involves death and rebirth. According to Stephen Hawking's famous theory, black holes are not truly eternal. They slowly evaporate, radiating away their mass over astronomical timescales. A small, primordial black hole from the early universe would have evaporated completely by now in a final, violent burst of energy. That burst would have been a cosmic firecracker, flooding its immediate surroundings with particles and radiation. If this happened after the neutrinos had already decoupled and formed their own background sea, that sudden injection of energy would have been a shocking disturbance. It would have reheated a local patch of the cosmic neutrino background, creating a hotspot in the ghostly sea. The neutrinos in that region would carry a slightly higher energy, a faint thermal scar from the death of a tiny, ancient black hole. The second, more subtle possibility involves life and gravity. Even before evaporating, a primordial black hole would have been a massive gravitational well. As the relic neutrinos streamed through the cosmos, their paths would have been bent by this intense gravity. The black hole would have acted like a cosmic lens, focusing the neutrinos and creating a localized overdensity, a subtle clustering of these phantom particles in its immediate vicinity. This would be a neutrino halo around an invisible gravitational anchor. Detecting either of these signatures would be a monumental achievement. Finding a statistical excess of higher energy relic neutrinos in a particular direction could be the ghostly echo of a long-dead primordial black hole. Alternatively, spotting an unexplained point-like concentration in the neutrino background map could signal the persistent gravitational pull of one that still survives today. This connection is a bridge between the quantum world of particles and the gravitational realm of spacetime warps. Confirming it would solve two mysteries at once, proving the existence of primordial black holes and giving us a new, indirect way to study their properties through their effect on the oldest particles in existence. The silent sea may be dotted with the ghostly graves and lingering shadows of the universe's most primitive monsters. The silent, ancient sea of neutrinos is not just a passive relic. It actively shapes the most violent events in the modern cosmos, carving its signature into the highest energy particles that streak across the universe. These are cosmic rays, atomic nuclei accelerated to nearly the speed of light by supernova and active galactic nuclei. When such a particle, a proton with energy beyond comprehension, travels across billions of light years, it eventually meets the cosmic neutrino background. This collision is not a gentle nudge, it is a cosmic roadblock. The ultra-high-energy proton smashes into one of the relic neutrinos, a ghost over 13 billion years old. The resulting impact is so powerful it forges new particles, creating a short-lived shower of exotic matter, primarily particles called pions. This process robs the proton of a tremendous amount of its energy, effectively putting a cap on how far the most powerful cosmic rays can travel. This predicted limit is known as the Greisen-Zatsepin-Kuzmin cutoff, or the GZK cutoff. It is a theoretical wall in the energy spectrum of cosmic rays, a direct consequence of the universe being filled with this primordial neutrino sea. Remarkably, our observatories have seen hints of this cutoff. The fact that we do not see an endless flood of the most extreme cosmic rays is in itself powerful indirect evidence that the cosmic neutrino background is real and permeates all of space. We are seeing the shadow it casts upon the most energetic particles, yet this confirmation opens new, deeper puzzles. The data is not perfectly clear. Some events seem to sneak past the GZK wall, arriving with energies that should have been stripped away by collisions with relic neutrinos long ago. Are our measurements of these cosmic rays imprecise, or is the physics more complex? Perhaps the neutrino background is slightly clumpier than we thought, leaving gaps in the roadblock. Or maybe the properties of the neutrinos themselves, their masses or interactions, are different enough to alter the effectiveness of this cosmic break. Every ultra-high-energy cosmic ray that reaches us has told a story, a narrative of its journey through the ghostly sea. By reading these stories, we are using the most violent particles in the present universe to probe the most serene fossil from the past. The silent background is not just being observed, it is being used as a tool, a cosmic filter that reveals its own properties by what it blocks and what it lets pass. What other invisible barriers has the universe erected, and what do the particles that slip through them reveal about the hidden architecture of reality? This primordial whisper might be the echo of a ghost we have yet to see. The 14th mystery introduces a truly phantom actor, the sterile neutrino. Unlike the three known types, this hypothetical particle would be a ghost among ghosts, completely immune to the weak nuclear force. It would feel only gravity, passing through the entire universe as if it were not even there. Yet its potential impact on the cosmic story is anything but silent. In the furnace of the first second, sterile neutrinos could have been the architects of a profound cosmic imbalance. The theory suggests they could have oscillated, transforming back and forth with the ordinary, active neutrinos. Crucially, these oscillations might not have been symmetrical. They could have produced a vast excess of ordinary neutrinos over antineutrinos, generating a colossal lepton asymmetry far greater than anything we currently imagine. This is not a minor adjustment, it is a cataclysm in the neutrino realm. This great lepton asymmetry would not have remained a secret. It would have imprinted itself directly onto the properties of the cosmic neutrino background we hope to detect. The relic neutrinos from that era would carry the scars of that ancient battle. Their energy spectrum would be distorted, their effective temperature altered, and the very way they mix and oscillate today would bear the signature of that primordial excess. Searching for these subtle distortions in the CNB is like looking for the shadow of a ghost we have never seen. It is an incredibly difficult task, yet it offers a path to proving the existence of sterile neutrinos that no particle collider on Earth could match. These machines can only probe particles that interact, leaving the sterile neutrino forever invisible to their direct gaze. But the cosmos itself provides a detector of unimaginable scale. If we can decode the faint patterns in the ancient neutrino sea, we might finally confirm that the universe is populated by a fourth, utterly elusive neutrino, a phantom whose only legacy is the dramatic tilt it gave to the cosmos in its first breath. This would force a complete rewrite of the particle physics rulebook and reveal that the true history of matter's dominance was written not just by the neutrinos we know, but by their invisible, sterile cousins. What other invisible architects have shaped the cosmos from the shadows? The universe's expansion rate is a number that should be set in stone, yet it is not. This is the Hubble tension, a crisis at the very heart of modern cosmology. We have two primary ways to measure how fast the cosmos is growing. One method uses the ancient light of the cosmic microwave background to calculate the rate from the early universe. The other observes exploding stars and other markers in our local, modern cosmos to measure the rate today. These two methods, each incredibly precise, yield stubbornly different answers. The universe appears to be expanding faster now than our best models of its infancy predict it should. It is as if we carefully calculated how fast a tree should grow based on its seedling phase, only to find the mature tree is significantly taller than our math allows. This discrepancy suggests a fundamental flaw in our understanding of cosmic evolution, and the silent sea of relic neutrinos might be the missing piece. The cosmic neutrino background is not a passive spectator to expansion, it is an active player. The density and pressure of this ghostly sea contribute to the total energy budget of the universe, influencing how quickly gravity can pull back on the fabric of space. Even a small change in our understanding of neutrinos could tip the scales. One compelling possibility is that there are more types of neutrinos than the three we know. Perhaps light, sterile neutrinos filled the early cosmos, adding an extra dose of radiation-like energy that sped up the universe's expansion in its youth. This would alter the sound waves imprinted on the cosmic microwave background, effectively changing the early universe's measurement of the Hubble constant to better match what we see locally today. Alternatively, the solution may lie not in the number of neutrinos, but in their behavior. If relic neutrinos decayed or interacted with each other through a secret force, they would have deposited their energy into other particles at a specific moment in cosmic history. This sudden shift in the universe's energy composition could have given the expansion rate an extra nudge, bridging the gap between the ancient and modern measurements. The phantom sea is a flexible component in our cosmic equations. By tweaking its properties, we can make the early universe's predicted expansion rate align with what we observe now. The true power of the cosmic neutrino background is that it offers a way to test these ideas. A future detection of this ancient sea would not just give us a number, it would provide a precise measurement of the neutrino density and energy throughout time. If that density deviates from the simplest predictions, it could be the key that unlocks the Hubble tension. The ghosts from the first second may be holding the answer to why the universe is rushing away from us faster than we ever thought possible. Deep within the first second of everything, the universe may have changed states as abruptly as water freezing into ice. The 16th mystery asks whether the cosmic neutrino background holds the fossilized tremors of these cosmic phase transitions. Picture the primordial cosmos not as a smoothly cooling soup, but as a substance undergoing sudden, dramatic shifts in its fundamental nature. One of the most significant of these was the QCD transition. When the universe was just a microsecond old, it was so hot and dense that quarks and gluons, the building blocks of protons and neutrons, roamed freely in a searing plasma known as the quark-gluon soup. Then, as the cosmos expanded and cooled, these free quarks and gluons suddenly snapped together, confined forever inside the protons and neutrons we know today. This was a change of phase for the entire universe, a rearrangement of the very rules of matter. The energy released by this sudden confinement would have sent powerful shockwaves rippling through the dense plasma. Any neutrinos that had already decoupled would have been battered by these waves, their paths and energies subtly scrambled. The specific pattern of this scrambling would be a unique signature, a ghostly echo of the quark-gluon plasma freezing into atomic nuclei. An even earlier and more profound transition is thought to have occurred at the electroweak scale. This is when the electromagnetic force and the weak nuclear force were unified as a single, majestic force. As the universe cooled, this symmetry broke, splitting into the two distinct forces we observe now. Such a fundamental rewriting of the laws of physics would not have been quiet. Theoretical models suggest it could have created vast, exotic structures like cosmic strings or domain walls, defects in the fabric of spacetime itself. The gravitational tremors from these defects would have left a distinct imprint on the neutrinos that were present, polarizing them in specific, predictable ways. This is the incredible promise of the cosmic neutrino background. It is not merely a thermal relic, it is a seismograph from the universe's most violent infancy. By analyzing the statistical properties of these ancient neutrinos, their minute anisotropies and any unexpected polarizations, we could detect the specific fingerprints of these primordial upheavals. A detection would do more than just confirm our theories. It would tell us exactly when and how these transitions occurred, revealing the energy scales at which new physics operates. It would be like finding the geological strata from the first instance of creation, allowing us to read the sequence of cosmic events with a clarity that light-based observations can never provide. The Silent Sea is a recording of the universe's most dramatic growing pains, a frozen record of the moments when reality itself cracked and reformed into the familiar laws we know today. What other shudders from the birth of the cosmos are preserved in this phantom medium? these phantom particles may carry a secret electromagnetic charge. This is the 17th mystery, the puzzle of the neutrino magnetic moment. We think of neutrinos as utterly aloof, immune to the electromagnetic force that binds our world together. They carry no electric charge, so they should ignore magnetic fields completely, flying through the cosmos on a perfectly straight path. Yet the quantum world is never so simple. A subtle loophole in the laws of physics suggests that neutrinos might possess a tiny, residual magnetism, a ghost of an electromagnetic presence known as a magnetic moment. It is a minuscule ability to feel and respond to a magnetic field. If this is real, it would transform our understanding of these cosmic phantoms. The effect is unimaginably small. The predicted magnetic moment for a neutrino in the standard model is so feeble it is essentially zero. It would be like a single grain of sand trying to deflect the course of a planet. But if we were to discover that the magnetic moment is larger, even by a tiny amount, it would be a direct signal of new physics. It would mean that neutrinos are not the simple, fundamental particles we thought, but are instead composite objects, or that they interact with hidden particles that amplify this ephemeral magnetism. For the ancient sea of the cosmic neutrino background, this tiny magnetic moment could have had cosmic consequences. These relic neutrinos have been traveling for over 13 billion years, streaming through a universe laced with magnetic fields. These fields are not the simple bars of a magnet. They are vast, turbulent structures woven through the spaces between galaxies, remnants from the earliest stars and cosmic shocks. If relic neutrinos have even a whisper of a magnetic moment, their journey would not have been straight. These cosmic magnetic fields, stretching for millions of light years, would have gently bent their paths. The ghosts would have been steered, their directions subtly scrambled over the eons. This would leave a clear signature in the cosmic neutrino background we hope to map. The subtle anisotropies, the hot and cold spots in the neutrino sea, would be smoothed out. The sharp features imprinted at the beginning of time would be blurred, as if the universe's most ancient photograph was slightly out of focus. Detecting this blurring effect would be like finding the cosmic fingerprints of those primordial magnetic fields. We could use the neutrinos as probes to trace the strength and structure of magnetism in the early universe, a history that is otherwise completely lost to us. But the implications run even deeper. A significant magnetic moment could have allowed these relic neutrinos to lose energy over time. As they twisted and turned in the magnetic fields, they might have radiated away a tiny bit of their power, causing the entire cosmic neutrino background to be slightly colder than our standard predictions. This would directly confront the mystery of its temperature, adding a new layer of complexity to our cosmic birth certificate. The search for this phantom magnetism is a search for a whisper within a whisper. It challenges us to build detectors so precise they could sense the most minuscule electromagnetic nudge on a particle that famously ignores such things. Finding it would not just be about the neutrino, it would tear a small hole in the standard model, revealing a hidden doorway to a deeper, more complex quantum reality. What other subtle forces are gently herding these ancient phantoms across the cosmos? The phantom sea is more than a cosmic fossil, it is a form of dark radiation. This label is not about shadowy particles, but about an invisible energy that fills the cosmos and influences its expansion through sheer relativistic pressure. The cosmic neutrino background is the definitive example of this, a persistent, ethereal energy that has been pushing against gravity for billions of years. Its contribution is measured by a crucial number known as the effective number of neutrino species, or NEFF. This number represents the total relativistic energy density in the early universe, and for a long time, cosmologists calculated a perfect value of 3, one for each known neutrino type. But the universe's ledger may not be so simple. Precise measurements from the cosmic microwave background have begun to hint that this number might be slightly larger than 3. This tiny discrepancy is a seismic event in cosmology. It suggests that the early universe contained extra sources of energy, something beyond the three known neutrinos. This is where the hunt begins. What could this dark radiation be? Perhaps it is the signature of the sterile neutrino, that ghost among ghosts, adding its own relativistic push to the cosmos. Or maybe it points to entirely new light particles predicted by theories like supersymmetry. It could even be evidence of primordial gravitational waves themselves, ripples in space-time that would have carried energy just like radiation. The cosmic neutrino background is the key to solving this. A direct detection and precise measurement of its properties would lock down the true value of any effect from the source itself, rather than inferring it from the blurred picture of the CMB. If we find that the relic neutrino sees density perfectly accounts for the expected three species, it would severely constrain the possibility of other light, exotic particles, forcing many speculative theories to rethink their predictions. But if the measurement reveals an anomaly, if the energy density of the CNB is itself slightly off, it would be a direct confirmation of dark radiation. We would know with certainty that the first second of the universe was populated by more than just the ghosts we know. The silent sea would finally tell us who or what its invisible companions were, revealing a richer, more complex particle landscape operating at the dawn of time. The moment of neutrino decoupling was a cosmic divorce of unimaginable scale. 1 second after the Big Bang, the universe was a dense, searing fog of particles, a plasma so thick that neutrinos were constantly bumping into electrons and positrons trapped in a violent dance. Then, in an instant on the cosmic clock, it all stopped. The expanding universe cooled just enough that the rate of these collisions could no longer keep up. The neutrinos, in a silent exodus, simply stopped interacting. They flew free, their paths barely altered from that moment on, becoming the permanent cosmic neutrino background we discussed today. This decoupling was not a perfectly sharp cut, however. It was a gradual fade out, and the precise physics of that fade out holds a critical secret. According to the standard model, we can calculate the exact instant and manner of this parting of ways. But what if the calculation is wrong? Even a tiny delay in the decoupling process, a mere fraction of a second longer of interaction, would have had a domino effect that changed the composition of the entire cosmos. The reason lies in what happened next, a pivotal event called Big Bang nucleosynthesis. This was the period, just a few minutes after the Big Bang, when the first atomic nuclei forged themselves from the primordial soup. The key player in this process was the neutron. Free neutrons are unstable and decay into protons if left alone. The only thing that gave them a fighting chance to form nuclei was the presence of electrons and positrons, whose collisions helped keep the neutron population stable long enough for fusion to occur. And here is the crucial link: the decoupling neutrinos were intimately tied to this balance. When neutrinos decoupled, they took a significant portion of the universe's energy with them, which directly affected the ratio of neutrons to protons at the start of nucleosynthesis. If neutrinos had decoupled even slightly later, interacting for a few moments more, they would have drained more energy from the electron-positron plasma. This would have cooled the universe faster, locking in a higher number of neutrons relative to protons. More neutrons mean more efficient fusion. The universe would have cooked its primordial hydrogen and helium differently. The most sensitive signature of this would be found in the relic abundance of light elements, specifically the amount of helium-4 and deuterium we see in the oldest parts of the cosmos. Astronomers have measured these ancient abundances with incredible precision. The observed helium-4 abundance is about 24% by mass. This number is a direct fossil from the first 3 minutes. Our standard models of neutrino decoupling produce a prediction that matches this number beautifully, but it is a delicate balance. If future observations were to find a slight discrepancy, if the primordial helium was just a fraction of a percent more or less than expected, it would point directly to a flaw in our understanding of that 1-second decoupling. It would mean the neutrinos did not leave the party exactly when we thought they did. This forces us to ask a profound question. Were there unknown forces at play in that first second? Perhaps the secret neutrino self-interactions or a magnetic moment we discussed before that gently held the neutrinos in the cosmic plasma for a heartbeat longer. The universe's oldest chemical fingerprints are waiting to tell us if our story of the first cosmic separation is complete, or if we are missing a crucial line from the opening page of the script. The silent sea of relic neutrinos did more than just fill the cosmos, it actively sculpted its grandest features. As the universe cooled after the Big Bang, these phantom particles were the first to achieve freedom, streaming across the nascent cosmos at nearly the speed of light. This incredible mobility gave them a unique and powerful role, one of cosmic landscaping. While dark matter was slowly pooling under its own gravity, forming the seeds of future galaxies, the neutrinos were acting as a counterweight. Their high velocities meant they could not be trapped in the small, growing gravitational wells of the early universe. Instead, they washed over them, a relentless tide that smoothed out the smallest ripples in the cosmic density field. This effect is known as free streaming, and it placed a fundamental limit on the minimum size of the first structures to form. Think of it like trying to build a sandcastle as waves constantly wash over the beach. The very smallest mounds, the tiny pebbles of density, are instantly erased. Only the larger, more robust hills of dark matter can survive the neutrino tide and continue to grow. This is why we do not see countless tiny, dwarf galaxies swarming around every large galaxy. The free streaming of the cosmic neutrino background effectively wiped the cosmic slate clean of the smallest structures. The imprint of this process is frozen into the large-scale distribution of galaxies we observe today. The cosmic web, with its vast filaments and immense voids, has a specific statistical signature. The number of small galaxy clusters compared to large ones, the sharpness of the filaments, all of these bear the subtle mark of that ancient neutrino smoothing. Future galaxy surveys, like those from the Euclid spacecraft or the Vera Rubin Observatory, are designed to map the cosmos in unprecedented detail. They will measure the clustering of galaxies with such precision that they could detect the specific damping effect caused by the mass of the cosmic neutrino background. It would appear as a slight suppression in the number of the very smallest structures across the universe. Finding this signature would be an indirect but powerful detection of the ghostly sea. We would be seeing the universe not just as it is, but as it was shaped by an invisible hand. The faint shadows of these ancient particles are woven into the very architecture of the cosmic web, a permanent record of how the fastest phantoms from the dawn of time dictated where galaxies could and could not be born. What other invisible constraints have guided the evolution of the cosmos, hiding in plain sight within the patterns of the night sky? The very laws of physics might not be as constant as we believe. This 21st mystery confronts a deeply unsettling possibility that the fundamental constants of nature could have changed over the vast expanse of cosmic history. We assume that numbers like the mass of the neutrino or the strength of the weak nuclear force are fixed, universal rules written in stone at the beginning of time. But what if that stone was slightly soft and the writing has been slowly shifting for billions of years? The cosmic neutrino background is the ultimate time capsule to test this radical idea, a fossil that formed when these constants were potentially set to different values. If the mass of the neutrino was even slightly different in the first second, it would have dramatically altered how these particles froze out of the primordial plasma. A heavier neutrino in the past would have decoupled earlier, changing the final temperature and density of the entire relic sea. The pattern of anisotropies we expect to see imprinted on the neutrino background would be subtly but distinctly warped, carrying a signature of that ancient different mass. Similarly, if the strength of the weak force which governs neutrino interactions was stronger back then, neutrinos would have remained coupled to the cosmic soup for a fraction of a second longer. This extended conversation would have smoothed their distribution even further, erasing the finest details in their map. The ghostly sea would be a palimpsest, with the original, sharp writing from inflation partially scrubbed away by a force that was, at the time, more potent. How could we ever hope to see such a faint distortion? A future detector capturing the cosmic neutrino background would not just measure a single number, it would analyze the full statistical tapestry of this ancient field. A deviation from the predicted pattern, a specific kind of smoothing, or an unexpected correlation in the neutrino sky could be the fingerprint of an inconstant constant. It would mean that the rulebook of the universe is not a static document, but a living text that has been subtly edited over time. The implications of such a discovery would ripple through every corner of physics. It would challenge Einstein's theory of general relativity and force us to consider that the fabric of spacetime itself may be more dynamic and complex than we ever imagined. The silent, pervasive sea of neutrinos passing through you could be the most sensitive record we have of the universe's evolving nature, a living testament to the fact that even the most fundamental truths of reality may have a history of their own. The phantom sea may be our only window into the quantum nature of spacetime itself. We have journeyed through mysteries of mass and matter, but the 22nd mystery asks if the cosmic neutrino background can answer the most profound question of all: what is gravity at its absolute smallest scale? For decades, physicists have struggled to unite Einstein's theory of gravity, which governs the cosmos, with quantum mechanics, which rules the atomic world. The place where these two titanic theories must meet is called quantum gravity, a realm of unimaginable turbulence. At scales a trillion times smaller than an atom, spacetime itself may not be smooth. Theorists suggest it could be a churning foam, a sea of virtual black holes and wormholes constantly bubbling in and out of existence. This is the hypothetical spacetime foam, a quantum froth at the foundation of reality. The problem is that this foam is thought to exist at such incredibly tiny energies that no particle accelerator we could ever build would be powerful enough to probe it. Its effects are presumed to be permanently hidden from our view, but the universe provides its own natural accelerator, one that operated for over 13 billion years. The relic neutrinos of the cosmic neutrino background have been traveling since the first second, and on their epic journey across the cosmos, they have been interacting with the fabric of spacetime itself. If that fabric is indeed frothy at the quantum level, these phantom particles would have been subtly affected. How could something as vast as spacetime leave a mark on something as ethereal as a neutrino? One possibility is through a process called gravitational decoherence. As a neutrino propagates through the hypothesized spacetime foam, its quantum wave function would be constantly jostled and disturbed by the microscopic churning. This would be like a traveler trying to walk in a perfectly straight line across a landscape that is constantly, randomly shifting under their feet. Over billions of light years, this effect would accumulate. The pristine quantum state of the neutrino, imprinted at its birth, would become slightly scrambled. For the cosmic neutrino background as a whole, this scrambling would leave a specific statistical signature. The delicate correlations between neutrinos arriving from different parts of the sky, the very patterns that encode the universe's initial conditions, would be partially erased. The neutrino sky would appear just a little more blurred, a little more washed out than our standard models of a smooth spacetime would predict. Another staggering possibility involves extra dimensions. Some theories of quantum gravity, like string theory, propose that our universe has more than the three spatial dimensions we experience. These extra dimensions are curled up into sizes far smaller than an atom. Yet, their existence could influence how particles like neutrinos propagate. A relic neutrino on its long journey might have its path ever so slightly altered by leaking gravitational influence into these hidden dimensions. This would manifest as a specific, energy-dependent delay in the arrival times of different neutrinos, a tiny effect that could, in principle, be teased out from a detailed map of the background. Detecting any of these signatures would be like finding the fossilized ripples from the shore of a quantum sea. It would give us experimental access to energy scales and physical regimes that are otherwise completely beyond our reach. The silent sea of neutrinos is not just a relic from the first second. It is a 13 billion-year-long experiment in quantum gravity. By learning to read its most subtle distortions, we might finally see the ghostly imprint of spacetime's true, turbulent nature, written in the paths of the universe's oldest travelers. The quiet balance between matter and its ghostly twin may be the most profound asymmetry of all. For every particle of matter, there should be an antimatter counterpart, a perfect mirror image with opposite charge. This fundamental symmetry, known as CP symmetry, should govern the neutrino world as well, yet the universe has already shown us a preference for matter on a grand scale. The 23rd mystery asks if this cosmic bias extends into the ghost realm, questioning whether the ancient sea contains an equal number of neutrinos and antineutrinos. The answer is not written in our current textbooks. While we label the different types of neutrinos, the haunting possibility is that the neutrino itself is its own antiparticle. This hypothetical identity, known as a Majorana particle, would blur the very line between the two, suggesting that what we call a neutrino and an antineutrino could be two manifestations of the same fundamental entity. If this is true, it would mean the cosmic sea is a sea of identical phantoms with no numerical difference to be found. But if neutrinos are not their own antiparticles, if they follow the standard Dirac model like electrons, then the question becomes urgent. Was there, from the first second, a vast numerical surplus of one over the other? A cosmic neutrino-antineutrino asymmetry would be a lepton number imbalance etched directly into the fossil record. Detecting this would require a sensitivity to the most subtle of cues. The relic neutrinos and antineutrinos, if they are distinct, would interact with matter in slightly different ways. In a detector like PTOLEMY, a primordial asymmetry could manifest as a slight distortion in the energy spectrum of the electrons released from tritium decay. It would be a tiny, persistent skew in the data, a statistical preference that points to an ancient, frozen-in imbalance. The implications of such a discovery would force a rewrite of our cosmic laws. A significant asymmetry would mean that a fundamental symmetry of nature, CP, was violated in the neutrino sector in the universe's first moments. This could be the very engine that drove the larger matter-antimatter asymmetry through a process like leptogenesis, making the neutrino the central character in the story of our existence. It would also place powerful constraints on cosmological models, as this ghostly imbalance would have contributed to the total energy density of the early universe, subtly altering the rate of its expansion. Finding a perfect symmetry, on the other hand, would be equally profound. It would tell us that the neutrino is indeed a Majorana particle, a being that is its own opposite, and that the great mystery of matter's dominance must be solved through other, even more exotic means. The silent sea does not just hold particles, it holds a cosmic ledger, a count of ghosts and anti-ghosts that could finally reveal why we are here at all. These phantom fossils might bear the scars of the universe's earliest cracks. Across the vast expanse of the cosmos, there could be defects in the very fabric of space-time, relics from when the fundamental forces of nature froze into their current forms. These are cosmic strings, hypothetical filaments of pure energy thinner than a proton but stretching across billions of light-years. They are not made of matter, but are topological knots, imperfections in the geometry of reality, left over from a violent phase transition in the first instance after the Big Bang. If they exist, their gravitational influence would have been immense, and the nascent cosmic neutrino background would have been the first medium to record their presence. As the sea of relic neutrinos streamed outward just 1 second into cosmic history, any cosmic strings present would have acted as immense gravitational lures. Their intense gravity would have bent the paths of these passing phantoms, pulling them slightly closer. Imagine a fine mist blowing across a landscape of invisible wires, the mist clustering just a little more densely around each filament. This is the effect a cosmic string would have had on the neutrino sea. It would have created faint, linear overdensities in the cosmic neutrino background, subtle trails of ghostly particles tracing the outline of these spacetime defects. The resulting pattern would be a unique fingerprint, a web of fine lines imprinted on the neutrino sky. This signature would be entirely different from the blotchy, random anisotropies generated by inflationary density fluctuations. It would be a structured, geometric pattern, a telltale sign of an ordered defect from the universe's birth. Detecting such a pattern would be the ultimate confirmation of cosmic strings, objects we have hunted for decades through their subtle effects on the cosmic microwave background and other probes, but have never found. The neutrino background offers a cleaner, more direct signal because it formed so early, before later processes could blur the sharp, linear features these strings would create. Finding these ghostly trails would do more than just prove the existence of cosmic strings. It would tell us precisely when the phase transition that created them occurred. The specific properties of the imprinted pattern, the spacing and thickness of the lines, would reveal the energy scale of that primordial event. This would open a direct window into the unification of forces, showing us the moment when the electromagnetic and weak forces, or perhaps even grander unifications, split apart, cracking the frozen fabric of the newborn universe and leaving behind these cosmic scars. The silent sea is not just a record of particles, it is a canvas upon which the deepest flaws in spacetime may have drawn their first and most permanent marks. Our journey through these cosmic whispers leads us to one final, profound horizon. We have unearthed clues about the universe's birth and its hidden structures, but what of the ultimate destiny of this ancient sea itself? The cosmic neutrino background is not a static monument. It is a dynamic entity with a future stretching over timescales that dwarf human comprehension. As the cosmos continues its relentless expansion, accelerating into an ever colder and darker epoch, the fate of these phantom particles is tied to a single critical property, their mass. For trillions of years, the universe will cool and the relic neutrinos will slow. Their incredible velocities, born in the fires of the Big Bang, will gradually diminish as the expanding space saps their kinetic energy. This is where their tiny, non-zero mass becomes the deciding factor. Once their speed drops sufficiently, their behavior will undergo a fundamental shift. They will transition from being relativistic particles, moving at a significant fraction of light speed, to becoming non-relativistic, sluggish ghosts wading through an increasingly empty cosmos. This change will transform them from a form of dark radiation, which pushes the universe apart, into a form of cold dark matter, which pulls it together through gravity. They will begin to cluster. The same gravitational wells of galaxies and dark matter halos that they once streamed through so freely will finally be able to trap them. Over eons, they will settle into these vast structures, adding their minuscule but cumulative weight to the cosmic architecture. This slow accumulation will be the final legacy of the cosmic neutrino background, a permanent, ghostly component bound to the skeletons of galaxies long after their stars have burned out. Yet this future is not the same for all neutrinos. The exact timing of this transition and the final distribution of this neutrino dark matter depends entirely on which neutrino is the heaviest, the very mass hierarchy we are still trying to solve. In one scenario, the transition happens relatively soon on a cosmic scale, and the clustering is significant. In another, it is delayed, and the ghosts remain a more diffuse haze for far longer. The silent sea will not vanish. It will simply change its nature and its role in the cosmos. In the far, far future, when the last stars have died and the universe is a cold, dark expanse populated only by black holes and the ashes of galaxies, the cosmic neutrino background will still be there. It will be a cold, slow fog of particles, the last tangible relic of the universe's fiery beginning, a final whisper echoing in the eternal night. Its existence is a testament to the fact that even the most elusive phantoms are subject to the grand, unfolding story of the cosmos, a story that began in a single, brilliant moment and will end in a silence punctuated only by these, the oldest travelers. From the monumental challenge of their detection to their ultimate cosmic fate, these 25 mysteries weave a single, epic narrative. They ask how we can weigh a ghost and what its temperature tells us about the Big Bang's first breath. They probe the fundamental order of neutrino mass and whether these phantoms gather in dark halos. They question if these particles are the reason we exist at all, tipping the primordial scales toward matter. We have explored the unsettling possibility of their decay, the search for a primordial imbalance in their numbers, and their potential secret conversations with dark matter. The mysteries reach back to the universe's violent inflation, seeking its tremors in the neutrino sea, and they map the subtle anisotropies of this ghostly fossil. We have considered their hidden social lives, their shadowy links to primordial black holes, and their role as a cosmic roadblock for the most energetic particles. The enigmas extend to sterile neutrino architects, a potential solution to the Hubble tension, and the fossilized shudders of cosmic phase transitions. We have asked if they possess phantom magnetism, if they are a form of dark radiation, and if their decoupling moment holds the key to the universe's first elements. They have shown us their power to sculpt the cosmic web, their potential to reveal inconstant physical constants, and their role as a probe of quantum spacetime foam. We have questioned the very symmetry between neutrinos and antineutrinos, hunted for their scars from cosmic strings, and finally peered into their ultimate destiny as a cold, dark fog in the far future. Each of these 25 puzzles is a frontier, a single thread in a tapestry that connects the smallest quantum rules to the grandest cosmic structures. The phantom particles passing through you are not just silent relics, they are a living library, a complex codex of questions that challenge our understanding of reality itself. They are the universe's oldest and quietest messengers, and their secrets are waiting. Which of these profound mysteries captures your imagination the most? Share your thoughts and wonder at the cosmic ghosts that hold the story of our beginning.